there is a thing that I like that's used in freshman chemistry lectures all the time, and I love this example, and actually it's on the first page of the first chapter of the book, and the example's called Caesar's Last Breath. And so it's a calculation you get the students to do. And the calculation is this. When Caesar took a lungful of air and spewed it out just before he fell to the floor dead after he was stabbed by Brutus, how many air molecules did he breathe out? And then you ask, if I now breathe a lungful of air in, how many molecules of that air came from Caesar's last breath? Just that one breath. Just that one breath. And the answer is, if you work out the volume of Caesar's lungs to the volume of the Earth's atmosphere, that ratio, and then you work out that fraction of the total number of molecules of air you breathe in on each breath, it turns out it's about 10 nitrogen molecules that came out of Caesar's lungs on that day will enter your lungs with every breath you take, which gives you some idea of how tiny atoms and molecules are. And so it's very hard to convey, and in fact I think even as scientists we fail to appreciate the scale of events we deal with because we learn exponential notation very early on. And you've got to remember every time you move the decimal point, that's 10 times smaller or 10 times larger. And they're an awful, so a nano is 9 zeros to one side of that decimal point. That's awfully, awfully tiny. And I think Caesar's last breath, for me, gives the students some idea of just how tiny molecules are. And that's the scale of the playing field in nanoscience. We've talked a lot about nanoscale fluctuations in biology. The thing about nanoscience that is so striking is that the things that occur at the nanoscale that make it interesting have implications for chemistry, biology, physics, materials science, engineering, you name it. There actually has not been a bringing together of the components of nanoscience like this. And it's very interesting to me to interact with people who have read the manuscript, because there have been lots of Xerox copies floating around and so on. And it's always been an eye-opener to some part of the community or the other who say, oh, gee, I didn't realize you could use this part for that. And so if you just go through the biology section, the statistical mechanics we do in Chapter 3 comes up again and again in the biology. The theory of chemical reactions is used to describe how enzymes work and so on. I think it is a very clear, integrated curriculum, and I would be very surprised if people said, oh, gee, this doesn't belong in here. Now, I've probably omitted stuff that somebody would say, yes, it belongs in here, but by the same token, I don't know how I could have increased the scope anymore. The reason I'm pleased with it is because in a given area, in applications areas, it's absolutely true that material you survey is going to be obsolete. Probably by the time I've taken my fingers off the keyboard, a large fraction of the material was obsolete because of the rate of development in this field. So I worked very hard to focus on the basic physics principles. It's why the first half of the book, or first third of the book, begins with quantum mechanics and statistical mechanics, and questions of how physics changes as you change the dimension of the object you look at, and so on. The reason I did all of that is because those are sort of never-changing principles. So when I illustrate a phenomenon like giant magnetoresistance, which is how the hard drive reading head in your computer works, I do it in terms of how changing the dimensionality of a magnet affects its properties. And that stuff is never going to change, whereas a giant magnetoresistance reading head might well be an obsolete item in a few years' time. And so I've tried always to emphasize the physical and chemical principles and use the applications as an illustration of them, even realizing that they're going to be obsolete. But I had one of the other reasons for producing the book was that I've had queries from people trying to teach courses like this. The other thing is, if you wander around the lab, you'll see dog-eared copies of the Xeroxed version of this book on my students' desks, because it is the sort of compendium of everything you need to know in nanoscience in a way. So they want to look a formula up, they want to look a piece of physics or chemistry up, and so on. This book sits there and it's a useful guide to them. So I've never been able to put my students, graduate students, through a training course that gives them the background what they need, because there wasn't such a course.